Okay, there's two additional methods that I'm just going to go through very quickly. These are relatively new methods. One of the things that our approach with rate transient analysis has really taught us over the years is that we have to be dynamic in our exploration of new methodologies that are out there. We always have to be on the cutting edge of what's available. And what we've found is these last two methods, the specialized and Wattenbarger method, have become critically important when we start to get into tight and unconventional gas. And I'm not going to go into a huge amount of detail in this course because this is our general RTA course, but there could be a whole separate discussion just on tight and unconventional gas. And these are the tools that we've found just in the past little while with looking at tight and unconventional gas systems have become really the most important tools that we have available now. So specialized analysis, again, I'm going to flip-flop back to the transient analysis. Ironically, even though I'm saying that this is sort of new and cutting edge, well, in reality, the specialized analysis is probably one of the oldest, long-standing pressure transient techniques that we have available. And that's what seems to happen a lot in reservoir engineering is we recycle old techniques but find new uses for them. In the past, a plot like this would have been used to diagnose or to analyze the transient production from a short-term well test and determine reservoir characteristics. And you would have called it a Horner plot or a square root of time plot. So we'd use it to determine KH or use it to determine XF root K and maybe some other parameters. Okay, and there'd be different ways of plotting this plot. But it would be a specialized plot or a straight line analysis. It's a technique that's been around for many, 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 many years. What we found is that when we get into ultra-tight and unconventional gas reservoirs, we start to get in situations where a long-term production data set looks the same as a short-term transient data set. Okay? They're, in a practical sense, they're two totally different things. But in pressure transient speak, permeability and time are very much interchangeable. So we can use these tools that were used for short-term build-up, drawdown, build-up tests and apply them to multi-year production data sets at ultra-low permeability, and they look the same. So what we've found is that the specialized plot, particularly the linear plot, which is a square root of time plot, is very useful for analyzing tight fractured gas wells. And sometimes the radial plot or the semi-log plot is useful also. It really depends on the geometry of the system. If you have linear flow in the system, you're going to see a straight line on the square root of time plot. If you have radial flow, you're going to see a straight line on the semi-log plot. But the purpose of these sorts of plots is to determine things like permeability in skin or permeability in fracture half-length. So we use them primarily for the transient data. They're a little bit like the equivalent of the flowing material balance, whereas the flowing material balance is a straight line analysis for boundary-dominated flow. The specialized plot is a straight line analysis for transient flow. So there's nothing too, earth-shattering about this, but we've found it to be very important contribution or an important complementary technique when we're looking at these transient data sets from tight gas. The other one I wanted to spend a little bit of time on is the Wattenbarger plot. And I don't have the right data set to show on here right now, but the Wattenbarger plot will show us systems that exhibit pure linear flow. So Wattenbarger is a professor at Texas A&M. He and his colleagues and students have done a tremendous amount of work with tight and unconventional gas looking at linear flow systems. And I'll just draw very quickly a picture of the sort of system that we're modeling with these type curves. Instead of circles or ellipses, Wattenbarger's method is actually, I don't know if that's going to draw it over here. Wattenbarger's method is something like a square or a rectangle with a fracture that penetrates all the way through the system. So what we get in these systems is linear flow, in other words, parallel flow lines coming into the fracture. And then as soon as the pressure transient moves out and reaches the end boundaries, we have an immediate transition into boundary-dominated flow. And it's a very simple model, but very effective in modeling tight and unconventional gas reservoirs. We see many, many, many production data sets that behave with these sorts of properties. And so these type curves become very useful, or have become very useful just recently in the last 5 years or so for looking at these tight gas wells.